Okay, good afternoon, one and all. We'll start the third session of the day, and it gives me immense pleasure to introduce this session speaker, who is my former colleague also in College of Engineering, Pune. Uh, Dr. Madhu Ranjan is an engineer and MBA graduate, having professional experience around 45 years, largely in steel industry, which span over 33 years. Besides this, he has relatively small stint in automotive industry also, which goes around 5 years, and in academics also, which span over 6 years. While the formative years his formative years were nurtured in the SAL at various locations, carrying assignment such as manufacturing and research. His career got catapulted into leadership role at the global renowned JSW Steel Limited, where he got involved in organization development right from defining vision, mission, and goals for the company and setting up world-class R&D facility. He took up the position of managing director at the Elring Klinger Automotive Company Private Limited, a 100% subsidiary of Elring Klinger AG, for over 4 years until January 2017. He has had a fairly successful transition across a wide spectrum of functions, roles, and responsibility throughout his career. The progression from hands-on to leadership role in globally recognized and respected steel companies and automotive component manufacturing company has instilled in him an excellent appreciation of entire gamut of functions, including organization development, plant operations, technology upgradation, and innovation through R&D. He had a fair share of thrust with academics, pursue uh, graduate level studies at the University of Cincinnati, US, obtaining MS 2003 and PhD in 2005 in material science and engineering. He has exposed to work culture in international scenarios in various industries in Moscow, France, and Finland, as well as University of Cincinnati, while conducting research and training. Sustained innovative achievement has resulted in several patents under his belt. He has 23 numbers of patents, 9 copyrights, and around 117 technical paper to his credit. Besides national level recognition in the form of Metallurgist of the Year award given away by Government of India in 2009 and Steel 80s award by Indian Institute of Metal in 2007. With this introduction, I welcome Professor Madhu Ranjan to this session and request him to give his talk on the topic Way Forward to Address Environmental Concerns related to coke and coal usage in steel production. So over to you, sir.
Yeah, thank you, Dr. Prakash, Professor Prakash Ranavre, for a very elaborate introduction. So let me start with what I will cover during this session. We'll talk about a little bit of steel making and the resultant greenhouse gas emissions. What are the greenhouse gas emission rates global as well as that of India? We'll also delve into the steel processing technologies which are responsible for CO2 emissions. And then we'll move on to a few strategies towards environmentally sustainable steel production and growth. And I have taken a few examples of steel companies, very renowned steel companies such as JSW Steel and Tata Steel, who have made strategic plans towards achieving net zero. And then we'll talk about conclusions. So moving on to the global scenario, and we'll also compare here what is the Indian scenario so far as steel production is concerned. The figures here in this tabular manner is that of 2021-22. The steel production globally was around 1.86 billion tons and that of India 120.3 million tons. And corresponding CO2 emission was 3 billion tons globally and 297 billion tons of India. The rate at which the emissions of CO2 happened globally was 1.91 tons of CO2 per ton of crude steel. And you can see that India's figures are higher at 2.36 tons of CO2 per ton of crude steel production. Then what is the contribution of steel industry towards the global greenhouse gas emissions? So far as the global steel industry is concerned, the average is 8%. In India, this average is higher at 12%. So steel demand is likely to keep going up. By 2050, the world steel is expected to grow to 2.5 billion tons per annum level, and that of India to 500 million tons if we go by the JPC and Ministry of Steel projections. However, these are concern areas, and it is desired that the steel industry total emission by 2050 must fall to a figure of around 500 million tons of CO2. And if we do that, the carbon footprint would be around 0.2 tons of CO2 per ton of crude steel. So from a level of 1.91, we need to aim to around 0.2 tons of CO2 emissions. So how and where are the contributors, and who generates carbon dioxide into the atmosphere? So iron extraction from its ore is a reduction process. We all know that. So iron is in oxide form, hematite, magnetite, wustite, and we need to take away the oxygen so that iron is available. Iron is made available. To do that, we need to have some fuel for generating heat to the level of fusion or to the level of melting. And we also need reducing agents such as carbon as solid and carbon monoxide gas and hydrogen gases. So unfortunately, the reductants at present that are available, they are all sourced from the fossil fuels, mainly coal, coke, and natural gas. So the dependence on fossil fuel is very, very high at the moment, and in future we need to move away from them. Additionally, like any other manufacturing facility, the steel industry consume a substantial amount of electrical energy for operating various manufacturing facilities. So the electricity is also sourced from the grid or internally generated within the plant campus. But in either case, predominantly fossil fuels are used for electrical generation. So overall, what we see here in this slide is that we are predominantly dependent on fuels which are generators of carbon dioxide into the atmosphere. Just a cursory glance of electrical generation in India. Total installed capacity is around 417 gigawatts, and 56 or 57% of the total energy is produced by fossil fuel. About 41% of our total energy in India is produced by renewable energy, and fortunately, this content is increasing fast. Nuclear component is only 1.6%. Now we have a look at the iron and steel making in India. We can split into integrated steel plant processing route and secondary steel route. So most of the integrated steel plant route, the first or the major focus is on the fulcrum of the industry, that is the iron making industry. So the iron making technologies that are being practiced is blast furnace route, There is a COREX, which is only at JSW at the moment. Then we have direct reduced iron, either produced from shafts or in the kiln. So these iron making processes, they depend on the raw materials such as iron ore, so lump sizes. The fines of the iron ore, they have to be agglomerated in the form of pellet or sinter. Then the iron ore also contains some gangue content or impurities. To take care of them, some fluxes are required, which is limestone here. And the fuel here is the coal. Part of the coal is a coking coal variety, which makes coke for blast furnace. But for COREX and other methods of iron making does not require coke. So the hot metal, which is the liquid iron, which is produced from the blast furnace as well as the COREX smelting reduction process, they become feed for steel making process. The most dominant steel making process is basic oxygen furnace and open hearth furnace. And if we look at the secondary route, we have electric arc furnace and induction furnaces, which act as mostly as a melting point. So the iron making process is a reducing reaction process, and steel making process is an oxidizing process. What we oxidize is the impurities. So these impurities are oxidized, and which goes into the slag form, and therefore pure steel is produced. The steel can be further cast, hot rolled, cold rolled, color coated, etc. down the line. So as we just now saw, the iron making process is a reduction process in principle, and the blast furnace route, this contributes almost 2/3 of the entire iron that is made in India. Okay, and the principal energy source is carbon in the form of coke or carbon in the form of pulverized coal injection. Okay, so the product is liquid hot metal, and impurities, they go in form slag, and slag and hot metal are easily separable in a blast furnace. The other method of producing iron is the direct reduced iron or sponge iron, we commonly say that. And they constitute about 1/3 of the entire iron that is made in India. So out of 47.85 million tons of DRI which was produced in 2021, about 79% of them were produced through DRI coal based. Okay, while the rest of 21%, they were produced using gases. The gases could be coke oven gas, natural gas, or gasified coal. So the iron is exposed to a reducing carbon monoxide gas at elevated temperature, and the resulting iron remains in solid state, which is called sponge iron. So in both these iron making cases, the fossil fuel remains the dominating force so far as the reductant is concerned, as also for generating adequate heat. Steel making route, about half of the steel made in India is through the basic oxygen furnace route. And here the hot metal from blast furnace is charged, and some amount of scrap is also charged as a coolant. Oxygen is blown into the converter, where the impurities such as silicon, manganese, phosphorus, sulfur, etc., they get oxidized and they go into the slag form. So the liquid steel, the resulting liquid steel, they are cast into various shapes like slab, bloom, billets, or ingots. The second variety of steel making is the electrical route. So one can opt for electrical arc furnace or induction furnace route. The arc furnace, their contribution is about 23%. And induction furnace, there are a large number of small size induction furnaces in India. Their contribution is 29% of the total steel produced through in India. So here the electrical energy is the main driving force to generate heat to melt the charge. So if we try to apportion how much of CO2 various stages of iron and steel making processes can generate, we can see that the coke making process, it takes about or generates about 20% of the total CO2 emissions. The agglomeration process like pellets and sinter, their contribution is 15% of CO2. The hot metal which is produced from the blast furnace, they contribute the maximum amount of CO2 emissions greater than 25%. In the crude steel making, that is steel making or secondary refining and continuous casting, etc., their CO2 apportioning is about 15%, and rolling, finishing, color coating, etc., about 15 to 20%. So here again we can see that more than 65% of the entire CO2 emissions are apportioned to up to iron making stage. So this is where the maximum effort will go towards making the neutral, carbon neutral world. Now let's have a quick look at CO2 generation at the world level. This data is from World Steel Association. The blast furnace BOF route, they are contributing 2.32 tons of CO2 per ton of crude steel. That is the intensity of CO2 generation. And this route has the maximum contribution to steel making, 71%. The scrap-based electric arc furnace, their contribution to steel making is 22% in the entire world. Fortunately, their CO2 emission rate is the lowest at 0.67. And making DRI through natural gas in combination with electric arc furnace, very small percentage of steel is made through this route. And their greenhouse gas emissions are somewhere between blast furnace and scrap-based EF route. Same if we want to compare with that of India, this is all India average for the year 21-22. The blast furnace in combination with BOF for steel making, their production rate is nearly half. Production share is nearly half, and their emission intensity is 2.46 tons of CO2 per ton of crude steel. If we consider the DRI route made from coal, and this DRI used in IF, induction furnace for steel making, their emission intensity is 2.30. If the coal-based DRI is charged in electric arc furnace, the emission rate goes up to 2.51, principally because this process route also consumes nearly 60% of hot metal from the blast furnaces. So the contribution of CO2 from the blast furnace is added up here. Then instead of coal, if we go for gas-based DRI and combine it with electric arc furnace in India, the emission rate is the lowest at 1.91. Here also we can see that about 30% of the charge is hot metal from the blast furnace, and rest is DRI and scrap. So overall, to produce 120 million tons in the year 21-22, the average emission intensity rate for India was 2.36, which is higher than that of the global average, which was 1.91. So we have a concern here and we need to address it fast. So overall, if we try to summarize, we are at the moment dependent on coal for steel production in a big way. It is not only supplying, major source for energy for the plant, it is also the major source for reductants And most of the captive power plants in India, they operate on coal. So now we see in the next couple of slides the average carbon dioxide emission intensities on all India basis for various production routes with breakup of the principal processes. And we compare that. We have a comparison here between blast furnace in combination with basic oxygen furnace route and coal-based DRI in combination with induction furnace. And we can find that the emission intensity of this route, blast furnace BOF, is high at 2.46, but the coal DRI and IF has lower total emission rate, 2.30. So here, this is a cumulative sum of the contribution from blast furnace, from basic oxygen furnace, from coke oven, from sinter plant, oxygen plant, and process emissions. So if we just try to see how much of CO2 emission rate so far as the stage up to iron making is concerned, so we sum up the BF emissions, coke oven emissions, and sinter emissions. This adds up to 2.18 tons of CO2 per ton of crude steel. And the rest, that is the steel making part, is only around 0.28. So the major chunk in the blast furnace BOF route, the maximum CO2 generation is up to the iron stage. For the DRI and induction furnace route, we can here also see DRI emission rate is 1.57, induction furnace at 0.62, and pellet plant at 0.04, and process emissions 0.08. Here also, if we try to compare the emissions up to iron stage, it adds up to 1.61, much less than what we find in blast furnace. But beyond this, also nearly 0.7 tons of CO2 is generated by the steel making process, largely induction furnace, which is run on electricity generated by coal. Here the two towers are, one is for gas-based DRI production in combination with electric arc furnace. This one is the least emission intensity so far as India steel is concerned. And the right side is that of, instead of gas, we have considered the coal-based DRI production and electric arc furnace for steel making. And this one is the maximum intensity, 2.51. In the gas DRI EAF also, if we see up to iron stage, the CO2 emission is about 1.31, and around 0.6 tons of CO2 is through the taken away by or responsible for the steel making portion. In the coal DRI EAF, the coal-based DRI process, here the iron making is 2.22 and only around 0.29 in the steel making stage. Okay. So one has to make a balance between which process is more suitable going forward in the future. So India's approach to net zero, again we will walk through India's approach with examples of two major steel producers of the country. One is JSW Steel, which produced around 24 million ton of crude steel in 22-23, and Tata Steel with a production of 20.8 million ton of crude steel. Both are top grade steel producers in the private sector. And JSW is among the most modern steel producers in the country. They use diverse technologies for iron making and steel making, and they are located in different sites in India. The JSW share of domestic steel production was 16.1% of the total steel produced in India in 21-22, but they account for around 15% of India's steel emissions. So they are slightly better than all India average. The present is about emission rate is around 2.36 tons of CO2 per ton of crude steel. So we will go through the roadmap prepared by JSW. Since I have a background of JSW, so please don't mind. I'll be referring to this company's um, data, and I'm thankful to JSW for sharing the data with me. So here is the timeline for prepared by JSW of reaching net zero by 2050. Okay. So what has happened is from 2005 up to 2023, uh, they have reduced their emission rate from 3.39 to 2.36, and we can say it is the current rate. Going forward, they have split the entire strategy into phase 1 and phase 2. So by 2030, they have planned to reduce the emission intensity to 1.95 by various actions, which we will see. And by 2050, they have various actions charted out, which will make it net zero. So first we see what they have done to reduce from 3.39 in 2005-6 to 2.36 tons of CO2 emission rate in 22-23. So the major actions were operating power plant on plant waste gases, beneficiation of iron ore to reduce gangue and therefore reduce slag rate and fuel rate, steam generation from waste heat recovery at different levels, installation of top pressure recovery turbines at blast furnace, installation of coke dry quenching CDQ at coke ovens. We'll talk about them in a little more details. And introducing pulverized coal injection in blast furnace, which have very good effect on fuel rate consumption reduction. They have also installed 225 megawatts of solar power energy at Vijayanagar. So they have gone for alternate or renewable energy generation as well. So if we want to see how PCI introduction in blast furnace has an effect of reduction in greenhouse gases, the JSW figure what I have obtained is that their fuel consumption total is 530 kgs per ton of hot metal, and this consists of about 340 kg of coke and 190 kg of pulverized coal injection. They have also found that the pulverized coal injection has a replacement ratio of 0.95. That is, if you charge 1 kg of coal, 0.95 kg of coke is reduced. The coal to coke conversion, when we take coking coal and make coke, the conversion ratio is 0.75. Rest 25% goes into the atmosphere. They are volatile matters. That means 1 kg of coal yields about 0.75 kg of coke owing to loss of VM. They are not lost, they are used elsewhere, but here the yield is 0.75 kg only. So by using these two ratios, if we are using 190 kg of pulverized coal injection, we are effectively reducing coke by 180 kgs, which in turn replaces coking coal of the order of 240 kg. Okay. So by charging 190 kg of PCI, they have reduced by 50 kg the consumption of coking coal. So there is a huge saving of 50 kg of coking coal. They are very expensive, and this saving of coal also has good potential of reducing CO2 emissions from the plant. Going further, the JSW plant has made a strategy to reduce the emission rate from 2.36 to 1.95 tons of carbon dioxide per ton of crude steel by 2030. That is in phase one. We can call it a short-term phase. And the broad actionable fields, uh, these are also globally recognized fields actually. They include improvement in process and energy efficiency, energy transition to renewable energy sources, use of alternative fuels, improvement in raw material quality, and enhancing material circularity. So we will look into each one of them, what exactly is planned within each parameter which I have mentioned above. So this is graphically JSW from 2.36. By energy efficiency, they want to have some reduction. By incorporation of renewable energy, they will reduce the CO2 emissions. By improving the material quality, there will be some contribution in reduction of CO2. And injection of natural gas in the blast furnace, that is alternative fuel, has a minor effect, but still they have an effect on reduction of CO2. And material circularity, like increasing the scrap usage in steel making, they also contribute. So if we sum up all the contributions mentioned here, we can, JSW hopes to achieve 1.95 tons of CO2 per ton of crude steel production by 2030. So we look at how the enhancing or enhancement in energy efficiency strategy uh, they have thought of doing, getting the end results. So one is coke dry quenching of coke. Of, uh, so one is waste heat recovery, one can do. Another is hot coke from coke oven is generally quenched with water, but in CDQ, the quenching medium is nitrogen gas. So the escaping nitrogen gas here, they have a lot of sensible heat, which is utilized for running boilers to produce power. So the coke produced with coke dry quenching method has very low moisture content, kind of 0.2%, as compared to around 4% in coke quenched with water. Now, with experience, the entire world has recognized that every 1% moisture in blast furnace burden raises coke rate by 4 kg. So you can imagine by reducing nearly 4% of coke, 15 to 16 kg of coke can be reduced with the help of CDQ technology. Therefore, this offers substantial reduction in CO2 emission rates. Then again, these are normally waste. So top pressure recovery turbines run the turbine from the top pressure of blast furnaces for power generation, and heat or energy recovery from solid and gas streams. So there are a lot of gases which are coming out of each processing route. There are a lot of solid waste also coming out. If those heat and energy from these wastes are captured, they will also help in improving the energy efficiency. And not the least, electricity saving by optimizing the processes. One can certainly reduce certain amount of electrical consumptions. Then optimal raw material selection and use, quality of iron ore and coking coal has a direct impact on energy intensity and CO2 emission. So beneficiation of iron ore and coal to reduce the gangue content or ash content really helps a lot in reducing the slag rate, reducing the coke consumption and coal consumptions. So switching to carbon lean or hydrogen containing fuels is an option, and increasing scrap use in the basic oxygen furnace will also help in reducing the emissions. Improving the yield. We know that there is yield loss in every process stage. For example, in steel making, you have certain yield losses. You have during rolling, you have yield losses. So like scale loss and all. If one can reduce that, the yield will improve, and therefore per ton of CO2 emissions will be on the lower side. So it is directly linked to reduction in energy intensity and raw material usage. Process reliability. By improving the maintenance and taking good care of the facilities which are run, the breakdowns and shutdowns can be minimized, and that will improve the reliability of operation of the equipment. This also helps in quality and process time improvement, thereby reducing energy per ton of steel. The B part of the overall focus area is on energy transition. So making electricity for steel making processes at present at JSW, they have an installed capacity of captive power plant about 1000 megawatt. 50% of this 1000 megawatt or 500 megawatt is generated from waste gases and heat generated from steel making processes. Remaining 50% is from burning of coal. Then the part of the electricity purchased from national grid, they are largely produced by using coal. Okay. Therefore, coal represents a major chunk of CO2 emissions from the steel production, and the only solution here lies in transitioning to renewable energy. We'll see that. Third one is alternative fuel sources. They have plans to inject natural gas into the blast furnace to reduce the coke requirement. And they have calculated that partial replacement of coke with injection of natural gas can save around 35 to 37 kgs of coke carbon dioxide per ton of hot metal produced. But the catch here is the availability of natural gas. India has very little of that. Then set up a gas-based DRI plant instead of coal-based, and the gas coming from Corex plant. Okay, the off gases from Corex, they contain carbon monoxide and some traces of hydrogen, so they are very good source for carrying out the reduction process in the DRI plant. So this they have planned to incorporate. Then actively improving material quality. It is known that the blast furnace performance improves when the gangue content and the ash content of coal is lower. It is normally found that a 1% increase in alumina in the burden raises the coke rate by 2.2% and decreases productivity by around 4%. So, setting up beneficiation plant to reduce the gangue content and the ash content from coal, which leads to reduction in fuel consumption, thus reduction in CO2 emissions. So by this method, the plant expects to reduce CO2 emissions by 23%. Finally, the developing processes for material circularities. What the circularity means is whatever the material has been produced and not used, can we find usage of that? So like scrap. Use of scrap in the charge of basic oxygen furnace, they have aimed to enhance it by 10% in the basic oxygen furnace. Okay, so more scrap you use, less of the hot metal you consume, and therefore the CO2 emissions are reduced. Secondly, the blast furnace slag and the BOF, the steel making slag, they should not be allowed to go waste. Utilizing this slag for cement making, already they are doing it, they want to enhance it. Okay. Coming to the longer term plan from 2030 to 2050, so there are two technologies in focus. One is usage of green hydrogen, and which is produced by renewable energy. Okay, and second one is carbon capture, usage, and storage. So there are processes which will existing processes which will continue to generate carbon dioxide. So such carbon dioxide, if we find a way to capture, use, and store, then the world will not see them into the atmosphere. So hydrogen can be utilized in two parts of the key parts of the steel making process. One is partial replacement of coke in the blast furnace. We know that we can't replace the entire coke. Some amount of coke is necessary to carry the burden in the blast furnace, and make DRI on hydrogen injection. So what is the challenge in partial replacement of coke in blast furnace? So here hydrogen instead of coke, they are the reducing agent. If we consider the carbon from the coke, so CO2 is the byproduct. Whereas if you inject hydrogen, then hydrogen combines with oxygen to make H2O, which is a major advantage. H2O is not at all harmful. So moisture comes out of the on top of the iron making process, blast furnace. But there is a catch here. The hydrogen reaction is endothermic as against exothermic reaction associated with coke. Therefore, to use hydrogen, you need an alternative source of energy as well. So introduction of hydrogen results in overall reduction in carbon emissions. There is an upper limit, though, to hydrogen blending, since a minimum quantity of coke, that is 250 kg per ton of hot metal, is essential to run the blast furnace. Okay. So hydrogen based DRI production. So the alternative route of making iron is DRI, direct reduced iron. So here hydrogen substitute the coal or natural gas for DRI production. So how do you do it? You first heat up the iron ore in a DRI furnace, and then hydrogen is passed over it. So the hydrogen combines with oxygen and liberates the iron ore into iron. Studies show that a natural gas DRI system, hydrogen can be blended up to 30% without much process change. So this will have a resulting similar reduction in carbon emissions. Another major area, as we discussed earlier also, is the scrap-based electric arc furnace. So instead of hot metal, we need to maximize the usage of scrap. This is emerging as a promising solution for reducing carbon footprint. Traditionally, steel production has relied upon hot metal or DRI, which use coal or coke as their primary raw material, resulting in significant amount of greenhouse gas emissions. But if we use scrap, then we can get rid of this part. Use scrap steel as their primary RM, which significantly reduce greenhouse gas emission. So by increasing the scrap-based electric arc, by having new facilities, when every plant is growing, so they plan to have scrap-based electric arc furnace as a steel producing unit. This will reduce the dependence on fossil fuels, and besides, this is also less capital intensive compared to the blast furnace route. Blast furnace installation is very expensive affair. Then alternative fuel usage. One can go for syngas, which is a mixture of carbon monoxide and hydrogen. Both are highly reducing agent. and they are produced from gasification of coal or from biomass. It can be used as fuel as well as a reducing agent in the steel production process. Another activity planned is having top gas recovery system, where top gas from blast furnace is recycled and used as a reducing agent. So the escaping gases from a blast furnace will have some carbon monoxide also, which have not been converted into carbon dioxide. So using the top gas from blast furnace also for other processes will will not allow escape of CO2 into the atmosphere. So the combination of syngas and TGR in blast furnace can certainly reduce CO2 emissions. So this is the last step which is mentioned here, carbon capture, utilization and storage. So whatever the iron making steps which releases carbon dioxide, from the gases the carbon dioxide is stripped into some solution, and in another stage of processing the CO2 is liberated from that solution and they can be stored, okay, transported and stored for use in food and beverage industry. Such gases recovered would have almost 99.5% purity of CO2. Okay. So we briefly also look at what Tata Steel's approach is there for. They want to achieve net zero by 2045. They have short term, medium term and long term strategies towards achieving their target of net zero. So I will not describe because most of them have been already discussed, but I'll just read them out. Steel recycling transition to complete circular economy. Steel recycling is like usage of scrap into steel making. Increasing the use of scrap in steel making. Optimization of energy intensity and carbon intensity. That is process improvements. Improving quality of raw material like beneficiation and all that. Increasing share of renewable energy. This is very important. Then medium-term strategy includes capacity addition using scrap-based electric arc. What they have when we say that the newer capacities will be scrap-based electric arc furnace type of steel making process. And shifting from coal to natural gas or coal bed methane, CBM. So this is something which was not there in JSW's approach, but they have planned to use CBM as well as natural gas if they are available. Then upscaling carbon capture, utilization and storage, and hydrogen-based steel making process. The piloting new technologies is in their agenda. The long-term strategy, scale up of some DRI smelting technology, adoption of DRI with present and future reductants. So to produce DRI, one can think of natural gas, coal-based methane, syngas or hydrogen. And production of green hydrogen. For such huge consumption, the steel plant needs to look into production of hydrogen for their own captive consumption. Carbon capture, utilization and storage dovetailing with the existing process. See, the existing processes of iron making, etc., which you cannot just scrap them, you cannot bulldoze them. So they will be there and they will be generating the CO2. What is mentioned here is that if those CO2 generation from the existing plants are captured, then of course we can minimize our CO2 contribution to the society. They also have research in their mind to produce advanced materials which requires less or which are less carbon intensive, and collaboration with technology companies and academia to achieve stage 1, 2 and 3. Briefly, we look at some trials which have been made internationally, such as this one is ThyssenKrupp of Germany, towards usage of hydrogen in blast furnace. Okay, so outlook here is the aim is climate friendly iron making, steel making production, injection of 25,000 normal cubic meter per hour and daily production of 4,600 tons. They have calculated that there is a potential of saving 20% CO2 per ton of iron which is made from the blast furnace if hydrogen injection is carried out. So they have a 100 megawatt electrolysis unit which produces about 1.7 tons of hydrogen per hour. And this is about 70% of the hydrogen required for the BF at Duisburg. So the electrolysis unit that they have, it can meet 70% of whatever the hydrogen requirement here. So they are at advanced stage of using hydrogen as part replacement of coal or coke in the blast furnace. By this method, they will produce 50,000 tons of climate neutral steel. This is a big way. There is another hybrid process which is being developed in Sweden, and basically they are also looking into breakthrough hydrogen iron making technology. So here if we look at the left hand side is the conventional iron making through blast furnace. The output is hot metal which goes into steel making, etc. On the right side is the new DRI process where instead of carbon fuel they will use hydrogen fuel. The resultant sponge iron and along with scrap will go into electric arc steel making process which will go for casting, rolling, etc. So their objective of hybrid process or of this company SSAB is to make fossil free steels by 2040 and switch to electric melting between 2025 to 40. Electric steel melting means have a electric arc furnace for steel making. Replacing coking plant and blast furnace with hydrogen electrolysis and direct reduction. So the coking plant and blast furnace will be done away with by incorporating this kind of futuristic technology. Then they look for electricity from renewable energy such as wind energy, and hydrogen storage they have thought of in lined rock caverns. Okay. So there are efforts also to make DRI using gases instead of carbon. So the left hand side shows natural gas in combination with hydrogen as the charge gas. So natural gas supplies the energy and hydrogen is the reductant. So here they claim that up to 30% of natural gas can be substituted by hydrogen without changing the process. The hydrogen may need to be preheated depending on quantities added. So since hydrogen is endothermic by nature, so some preheating will be required to the extent that how much of hydrogen you are charging or how much of hydrogen is replacing natural gas. Okay, rough calculations from for Cleveland Cliffs plant, 1.6 million ton per annum